Whether you're an experienced engineer or someone diving into electronics for the first time, you've likely used or at least heard of op-amps before. In this video, we'll dive into the device and take a look at the comparator circuit, a common application.
At Gentium Electronics, we believe that every problem has a solution, so we strive to make learning about electronics easier and more accessible. Our products and videos are made for creators who share our passion for technology and education equity. Now let's get right into it.
The operational amplifier is a powerful device used in a range of analog circuits. It is primarily used to amplify an AC signal, a voltage that oscillates in time. It has 5 main connections: the supply voltage terminals, 2 inputs, and an output. The input on the top is called the inverting input and is labeled with a minus sign. The input on the bottom is called the non-inverting input and is labeled with a plus sign. Op-amps have what's called a differential input, meaning the input to the amplifier is the difference between these inputs. The connection at the point of the triangle is the output. From this output, the voltage will be equal to the difference between the inputs multiplied by a gain factor, A, meaning the output will be amplified. The output voltage is limited by the value of the supply voltage. There are 3 main rules of ideal op-amps, which can help us understand their behavior. First, in an open loop, the gain of an op-amp is infinite. This means that regardless of the input signal, the output will be infinitely larger in magnitude. Of course, in reality, the gain is limited by non-ideal effects. The second rule is that no current flows from the inputs into the amplifier. As shown in the diagram, the input and output can be thought of as separate circuits. Finally, when the output is fed back into the input, the voltage between the 2 inputs will always be the same. The gain factor of op-amps is typically too large and varies too much with manufacturing to be useful as is. Therefore, we use special circuits to specify the gain we need. These circuits include the inverting and non-inverting op-amps, which are shown here. The gain is controlled by changing the resistor voltage drop in a feedback loop. Stay tuned to learn more about these in a future video. Another very important use of op-amps is the comparator. As the name suggests, it is used to make a comparison between our input voltages and output a useful result. But what exactly is an op-amp comparator? Let's dive into this when we come back.
Hey there! If you're enjoying this video, you should check out our introductory robotics course. We've noticed that while there is plenty of information on the internet about robotics and controllers like Arduino, there are no tutorials that provide an easy-to-understand approach to learning these topics. Our course walks you through the process of programming with Arduino step by step, giving you the freedom to create your own robotics projects or help you succeed in a career in engineering. If you're interested, click the link in the description to get started. Now let's get back to the video.
So, what is an op-amp comparator? Earlier, we mentioned that the open-loop gain of an op-amp was infinite in an ideal case. In reality, this gain is above or around 100,000. You may be wondering if there's any use to such a high gain. Well, this is in fact the fundamental concept behind the comparator. A comparator is a circuit that has 3 different output voltages: 0, the negative supply voltage V-, and the positive supply voltage V+. There are no feedback loops in this circuit as we want to maximize the amount of gain. Recall that the op-amp uses a differential input. From this, we can determine the output of the comparator. If both of the inputs have exactly the same magnitude, the output of the comparator will be 0, although this is highly unlikely in reality due to factors like electrical noise. If the inverting input has even a slightly higher voltage, that difference will be scaled by a factor of around 100,000, and the output will be equal to the negative supply voltage. Conversely, if the non-inverting input has a higher voltage, the output will be equal to the positive supply voltage. This circuit has a number of applications. If you set the inverting input to a reference voltage, such as ground, you can detect if your small input is higher or lower than this reference, using the larger output to turn on an LED, for example. Since they have a binary output, comparators can also be used to convert analog signals into digital signals, serving as an analog-to-digital converter, or ADC for short. Finally, comparators can be used to produce square waves from sinusoidal waveforms, which are generated by something like an LC circuit. Square waves are used heavily in the functionality of digital circuits. By watching this video, you have learned what an op-amp is and how it works as a comparator, a powerful and versatile circuit for comparing inputs. As we've discussed, a comparator is not the only use for op-amps. So we ask, What do you use or want to use them for most in your projects? We would love to hear your thoughts in the comments below. In the next video, you will learn how to set up your own op-amp comparator circuit with step-by-step instructions you can follow at home.
If you liked this video, check out the rest of our channel for more robotics lessons and educational content. We want education about electronics to be accessible and easy to understand, so if there's a topic you want us to cover, please leave a comment down below. Remember to leave a like and subscribe to stay up to date with the rest of our electronics tutorials and to continue learning how electronics work. Thanks for watching!